So good morning, everybody. Thank you for joining. Thanks for the organizer for the invitation. And I'm very, very honored to be here with you guys today. I'm very happy to talk about something about our work on computational fact-checking. And first of all, I would like to share, oh, it's not working. Okay. A little story that I actually attended the EDBT summer school in 2004, some time ago, as a student. And this was organized in the south of Sardinia, which is an island in Italy, by my advisor at the time, a PhD advisor. I was a PhD student. And he told me, would you like to come? You know, you can drive the people to the airport like the speakers. You can help me out, right? And I say, sure. I mean, we go to Sardinia and it's going to be, you know, I'm going to be driving these beautiful roads right by the sea. But ultimately, I spent most of the time stuck in a queue because you can imagine that Sardinia in June was very, very busy. Anyway, I have beautiful memories, and I'm sure that you guys are also having a good time meeting people that, you know, you will stay in touch with them a long time. So today, I'm going to cover some of the work we have been doing in this context, and I'm going to start with the motivation. Then I will introduce you to the pipeline for computational fact-checking, how we go through different steps to identify the claims we want to verify and the evidence to check them and how we verify. Then I will dig a bit more into the details of the methods, especially the data-driven methods for doing this verification. I will talk a bit about the role of the humans, how to do hybrid systems, and then I will discuss a bit the status of this kind of research. Okay, before starting, I have actually a disclaimer. So first of all, today is going to be a bit different from what you have seen in the previous days, because we have been focusing a lot on database techniques, of course, given the context of the school. And I'm going to use some of the notions that you have seen in the previous days, but I'm going to talk mostly about problems and solutions that are at the intersection of different fields, and specifically between database and natural language processing, which is something that I've been studying for a few years now, and I'm looking at how to use database techniques to solve some of these problems. So we're going to go a little bit, you know, in a different territory. So I hope that it will be interesting for the people who are not familiar. And we're going to touch also on other subfields of computer science, such as CSS, that stands for Computational Social Science, which is like people doing interviews and surveys around these problems and information retrieval. Okay, so I'm going to use some terms during the talk, and I'm going to try to do a good job introducing them for everybody so that you are comfortable. And also I have a second disclaimer that I know, I mean, we are all aware that this is the last day after you have taken many classes. It's going to be 2 hours without a break, and it's 8:30 a.m. So I decided to keep it a bit more at the high level to give you a good overview, and I'm going to point you to the papers for the more technical details. Okay, so it's going to be a bit different. I hope you like it anyway. Okay, so in terms of motivation, there is a keyword that you probably have heard a lot, fake news, right? That we don't like too much in academia because it's very vague. So, but it is something that people used to refer to, say, about, you know, fake stories about the elections, trying to steer the elections in the US. We have seen this. We have seen the same for the Brexit referendum. There is a clear evidence that some false stories were, you know, steering people towards one side or the other, one side mostly. And there is evidence of false stories going in social networks with sometimes tragic consequences. And then there is a story very strong about vaccines, but it's not the one that you may think. Those are all stories from 2019, up 2019. And even at the time, there was a lot of emphasis on the problem of people claiming that vaccination is not needed for many diseases. And online, they found a lot of consensus. So in countries like Italy and France, we have a drop in the percentage of people covered by the measles vaccine. And you know, this led to outbreak, people dying, and this is all because of rumors spreading with a strong effect online. Okay, so you may think, okay, this is, you know, for dumb people. I'm a smart guy. I will never fall into misinformation, right? And believing it or even spreading it. So I encourage you to put down your phone for a second, don't look at your laptop for solution, and take a moment to try to answer this question. Do you believe that these facts are true or false? So the first one, sitting too close to the TV damages your eyes. And you should drink at least 8 glasses of water per day. Carrots are good for your eyes, and we use only 10% of our brain. So how many people believe that the 4 of them are true? Ah, you guys are smart. Okay, what about 3 true, 1 false? 2 and 2. Okay, 3 false, 1 true? All false. Okay, so actually the correct answer is that all of them are false. So I can leave you as an exercise. It's not a proof of a theorem, but you can go online and check this. But all of them are actually false. I checked as carefully as I could. And it's interesting because there are stories behind this, right? I mean, it's not that we are just, making mistakes because we are lazy or not careful. But for example, for the story of the carrots, it's very interesting because it is coming from the fact that during the Second World War, in the UK, they got much better at shutting down the Nazi bombers. Okay, and it is because they had a much better radar system, but they didn't want to disclose this information to the Nazi. So what they did is that they started a misinformation campaign saying that, our fighter pilots, they're getting better because they eat a lot of carrots. So they have a sharp vision that it's even effective at night. Okay, so this is really interesting because, for me, at least before checking, I thought that it was true. And what's interesting here is that indeed, for many misinformation stories, there is a grain of truth. It is true that if you have a deficiency in vitamin A, your eye vision can improve because of carrots, but it's not that in general you need this and it's going to do wonders. Okay, so this campaign is real. I mean, they were saying, it's a matter of life and death, and if you eat carrots, it is changing your vision, and that's the solution to the problem. Okay, so I think it's interesting because it really digs into the fact that these things are tricky and they can really go into our mind in ways that we don't expect. And I think that we all witnessed it, unfortunately, in the last 2 years, the fact that maybe we have been actively using, false information and spreading it on WhatsApp or with our friends when the pandemic started, right? You may remember that at the beginning, there was this story that maybe we don't need masks because, it's not going to help. At least I remember it very clearly at the very beginning. And indeed, the World Health Organization was aware of this problem since the beginning. It is something that came up at the very beginning of the pandemic in 2019. And across the 5 main challenges, they listed the challenge of providing accurate information and fight the infodemic, where infodemic is this abundance of information and you don't know actually what sources to trust. You don't know what is reliable, okay? So those are big problems, right? And I hope I convince you that they are in our life and they have impact. And of course, most of these problems, they are spreading because of the new media, specifically the web, social media. And many people look at the main web players as someone who should come up with a solution, right? And they have pressure to improve on this. So for example, in Google, if you put a claim that has been already verified by some fact checkers, I will talk about them in a minute, Google has some special metadata telling you, for this claim that the sun kills the coronavirus, there is actually a page stating that it is false by the national academies, and you can click here and you get a report with the evidence that we have that this claim is false. Okay, if you use Facebook, they studied very different interfaces, but one interface, it's about the fact that you may try to share a story that is false, and they know this because they have seen this before, they've seen that link, for example, and they say, maybe before sharing this, you want to check these other sources, alternative sources to, make sure that you get all the aspects, and you can say, okay, let me see the website of some of the fact checkers, and or otherwise you can post anyway. Okay, so they are giving these alternatives. And finally, this is the first tweet that got this label, again, with getting more information about a fact, because this was this politician claiming that, voting by mail was a bad thing, you should not do it. And there was a lot of evidence that it is not true. So they started putting some labels to help people inform that, you may get more details about how this really works. Okay? So who is doing this work? Who are these fact checkers? So there are a bunch of organizations all around the world. I try to cover, here we have US, UK, India, Italy, France, just some examples of the NGOs or journalists, newspapers, where they have a group of people that every day they meet in the morning and they say, okay, what are the stories we need to verify today? They study it and they put online 1, 2 articles about the claims that are going around, and they evaluate that they are dangerous and they verify them and share the debunking, it's called, okay? So for example, imagine that there is a crazy story saying that someone won the election despite the evidence, and this can be, for example, spreading on Twitter, or it can be on some newspaper going around. So what these people do is that they take the claim and they say, okay, we study it, we believe that it's not credible. This is done by one of these partners. It's coming from the US, and there is a link with all the details, right? So this little bit here, this piece of information, it's actually that is shared online by using HTML tags. And so the page with this information can be indexed by Google or other sites. So there's this little format called claim review, so that we have a collective corpus of checks done by the fact checkers. Okay, so this is important. I will go back to this because some computational solutions rely on this strong corpus of things that we can trust. Okay, so far so good? Makes sense? Okay, good. So this fact-checking organization, there are around 300 active in the world. These people are amazing. I've interviewed a bunch of them. They're really serious, dedicated, they believe in what they're doing, and they are very, very good. Usually, I would say that you can trust what they write. However, there is a problem here. You see that 300 groups doing 1, 2 fact check per day is not going to cover the huge amount of false information that is created every day. So of course, the challenge here and the motivation for what I'm going to present is that manual fact checking cannot scale to the amount of information that is out there, new, created every day, circulating, shared, etc. Okay, and you don't have to take my word for this. There is a lot of evidence. For example, this is from the middle of the pandemic. In the Wall Street Journal, they reported that at Facebook, where they had at the time 30,000 content moderators, 30,000 people checking the content online, they cannot handle the amount of false claims about coronavirus, and they were maxed out. There is evidence that where a false claim is going around in the social network, it takes up to 22 days for the platform before they recognize and eventually downgrade it or remove it or put a label. And this is for English. For Italian and Spanish, there is evidence that it keeps going forever. They don't detect it, okay? So this expert-based fact-checking, of course, has clear advantages. This relies on the humans, so they have high credibility because they are certified, they have experience, they can handle any kind of claim, and they can produce detailed evidence of why something is false, right? So this is the best you can do in terms of fact checking. And there are, of course, some disadvantages. As I mentioned, the scalability, the latency, because they need the time to identify and to decide and to study and to publish. And there could be some human bias. That's also something to consider. And of course, there can be domains where they're not experts. Suddenly, they become important, like the role of ventilation in rooms suddenly become something very important, and they are not all experts or epidemiology or something very technical, right? So this is something also that creates problem. So all of this is to motivate. Oh, please. What's the role of journalists? So they absolutely. I mean, usually, like in Le Monde, they have a group that is called Les Décodeurs here on the right, and it is a group of journalists within Le Monde. And at AFP, which is one of the biggest, the news agency, they also have a very strong group of people that are, fact checkers all around the world, so that they can verify. So this goes hand in hand. But even if you look in some newspapers, you will notice that it's not the journalist itself. Like there is always a third. So there is the journalist creating the story, and then there is a team of fact checkers verifying it independently. So I didn't mention this, but it is an old practice coming from good journalism to verify the facts before publishing. The problem now is that we are all publishers online, and so the people are going after us, trying to stop us for putting false claims. Okay, sorry, any other comment, question? Okay, yes.
Very often in the case it's not about presenting the whole text, but rather about presenting very specific, being cherry picking, presenting those facts that are serve your ideas. So when you talk about text section, you talk also about extending the knowledge or providing some extra information which may be relevant.
So this is super spot on. I'm not covering today, given the time, the topic of detecting cherry picking. There are some good papers, and I put one in the references, and I have some extra slides on that. So if we have time, I will cover also cherry picking, which is a great topic. So, but it's not part of the main talk because of time. And I'm going to talk a lot about evidence and how you can also spot some cherry picking, but there are specific papers for that. So if there is time, please remind me at the end, and we will go over that. Okay, so the very general problem statement here is that we have some content, and we would like to assess if it is true or false. Okay, so in 2019, when I started looking at this, as you can imagine, it is a problem that you can take from many different angles. For example, in terms of content, right? You can think about text. We're going to focus mostly about text today, but it's true for images, video, audio, etc. Right? And you can take it from very different technical angles. So people in 2019 started having workshops in very different venues. For example, we had one in www, but also in the information retrieval, NLP, KDD. There started to be some events about, we can take this problem from NLP angle, data angle, information retrieval angle, because it's a difficult problem, as we will see. And then now, after 2019, with the infodemic and everything, there are new venues from different angles popping up every day. Okay, so this is something that people are studying a lot. And I'm not going to cover all the possible approaches today. I'm going to focus on something that is mostly data-driven from relational data and graph data, given our context. But just to give you a little bit of a feeling about the fact that there are alternative ways to look at this, I'm just going to mention a couple of approaches. So one approach is to say, no, I'm not going to verify the content piece by piece, but I'm going to go to the source. So let's try to design methods so that we can characterize the sources as precisely as possible in terms of veracity, if they have partisan bias, so that when I see a piece of content coming from some source, I can say, you're not going to trust this. Okay, so this is related to truth discovery in databases. So this is something that, there is a lot of research also from the database angle. So this is characterizing the sources. It's one possible way. We're not going to talk about this today. Another possible approach is to focus a lot on the network. So there is a lot of emphasis on saying, okay, if you look at the network, you can start to model the belief. You can start to model the nodes that that they are spreaders, so you can see the patterns. And it is all valid and very well studied. Okay, so it is more at the network level. There are many papers. I put some citations and some references. Well, I'm not going to go over this in detail, okay, but just to give you a feeling. What we are going to look in more detail indeed is this computational fact-checking pipeline. Okay, so as you see, we are at the very high level here. There is some input that can be text, audio, image, video, and at the end, we would like to produce some labels. Okay, and here, unfortunately, there is no a very nice model to look at this and say, okay, you know, we have a clear problem statement. There are many sub problems and they interact with each other. And the first one is that you have some content. Imagine an entire video, or maybe we can stick to text, which is easier to understand. And so we have a paragraph, and we want to find the claims in this paragraph that are worth checking. So what are the claims that we believe that they are potentially harmful enough to be important to verify, and then they can be checked? Okay, so we're going to see this in a moment. So then there is this step that I already mentioned where you want to verify that, okay, you identify some claim, you want to see if it has already been checked by somebody else, like the claim review that I mentioned a moment ago. Okay, and this is tricky also because you may want to do this in multiple languages. So that's a big problem. And okay, there is a new claim. It has not been fact-checked, it's a fresh claim. So you want to gather all the evidence that you need in order to debunk it automatically. Okay, so you want to go over trust sources of data and try to collect all the evidence. Once you have this evidence, then you can go to a step that suggests if you believe this is correct, incorrect, in a simple setting. The reality is a bit more complex. There are multiple possible labels at the end for the content. It may be the case that it's partially correct. There is not enough evidence, out of content, cherry picking. So those are possible labels that you give that go beyond the true false. Okay, which is a bit simplistic, but in general gives the idea. So far, so good? Okay. Okay, so let's start and get a bit into the details. So those are the systems that produce a checkworthiness score when in the first box, so that the checkers, for example, then prioritize the claims, or we can use it in some monitoring of what's going on in our social network. And the first system, actually, this is from a database group in the US. It's called the Claimbuster. And this is a very standard machine learning system that is trained on example. So it's a supervised solution where they have annotated sentences. Some of them are non-factual, some of them are unimportant factual, and some of them are checkworthy. Okay, so they identify some features based on sentiment, name, entity that are present in the sentence, part of speech text, words, claim length. So there are some features. So I move into the standard machine learning classifier setting where you have some features, you have some examples, you train a model, then given new test data, you can run and try to identify new checkworthy claims. Okay. Now, this is what they did in 2017. Meanwhile, something happened, and now there are many other models to do this checkworthiness estimation, and the vast majority of them are based on pre-trained transformers, such as Bert and Roberta. So if you're not familiar with pre-trained transformers, I'm going to spend one slide to give you a background, and I feel honored that I can tell you this story because it's an amazing story about how people in NLP went from many tasks, almost all the tasks, from like 70, 80 accuracy to 95, 99. Okay, so a few years ago, it happened that people came up with this idea of saying, okay, now we have enough text and enough computation power. They came up with a new way of creating these models for NLP. And by the way, these models that I'm discussing here, they can also be used over structured data. And we're going to have a tutorial on how to use transformers with the relational data in VLDB in September. So I'm not going to talk about this today, but you can use this technology also for structured data and many other things, images, etc. But it all started with text. And And the idea is the following. You have a lot of text that is available. Imagine the entire web, or just Wikipedia, or your specific corpus. You work in a company and you have all the manual, the notes from the clients, the emails. So you have your text corpus. And so let's define a sense-supervised task for training this model without giving training data, but we use the text to create the example. So for example, you may have, I don't see a marker. Yes, here, sorry. Something very simple like the, oh, hey! Not the first one. Sorry, guys. I'm very sorry. Cat is cute. So in the sense-supervised training, they mask this word, so they remove it and they tell to the system, okay, try to predict the word given the context in the sentence. So you can do this for every word in every sentence, in every paragraph, in every document. And the model is learning. So by modeling the probability of having some words after, surrounded by other words, it will learn that probably here it's cute, beautiful, but it will not put dangerous in the top predictions. Okay, so this is interesting because this is completely self-supervised. You don't need to come up with the examples. But by doing this over a huge amount of text, it slowly learns about the syntactical pattern in the sentence and the semantic of the words in the sentence. And they understand the relation between cat and other words. Okay, so over many, many documents, this brings to a neural network that now is extremely good at this task of mask and prediction of words in sentences. Okay, which per se is not a very useful task. But the magic here is that now we have this pre-trained model by Google, Facebook with billions of parameters. So it's a huge model. And now we can do a new task on top of it. So we use it as a starting point and we say, okay, I'm going to give you a little bit of training data for another task that is about language, such as, for example, detecting if a message is spam or not spam. Okay, I mean, we're all familiar with this. Email, you want to classify it. So traditionally, you will use the features, like I mentioned a moment ago, right? The length, the keywords, etc. Here, you don't have to do the feature selection. You just tell the model, okay, I'm going to give you a little bit of examples. I mean, this works even with few shots, which means with few examples, but let's say a few thousand. You do the fine-tuning, which is the task of taking this model and change it according to the new classifier task. So some of the weights in the model are going to change. So all the knowledge that is coming from this exercise, it's already there. So you don't need to specify that, I don't know, pills and drugs, they are related semantically, because it's already here. So if you train it with the pills in your training data to say that it's spam, when you see drugs, it knows already that those are closely related semantically. Okay, so you do the fine tuning, you get a new model, and now you can use this new model on the test data. So why I'm spending time on this? Because this is extremely powerful. Most of the solutions that I'm going to mention in the rest of the talk, they're based on this architecture where you get a pre-trained language model and then you design the right task to do this fine-tuning and you can use it in many, many target applications. Make sense so far? Okay, great. So as I mentioned, for finding the word checking claims, they rely on this kind of solutions. Now, it is the standard. And the second box here is to identify the false claims that are spreading, despite we have already some claim review that it's able to say, you know, this claim is false. Okay, so we want to do this so that we can eventually identify these as soon as possible and stop them, right? And the idea is that you have, again, the example we had before, there is a claim saying something, you have a big corpus of these checks done by the claim review and the fact checkers, and you want to identify the match against, you know, of this claim, if there is a match over the claim review. So there are many methods again. The first paper that is worth mentioning is this paper from ACL in 2020, where they use BERT and BM25. It is something like unsupervised like TF-IDF for matching based on the frequency of the words. And they also came up with some data sets that are widely used in this context, like tweets that are matched against one of the fact checkers that I mentioned, Snopes, or political debates, again, matched against some PolitiFact corpus. Okay, so this is the task of matching of previously checked claims. So we're still in the second box. We can go to the third one. Here is the context where, okay, you try to match it, it didn't match, so it's a new fresh claim, okay? So we need to find the evidence to help the human or the system decide if it is true or false. And this evidence, you can imagine that can be in large collections, so in a large video, in a large stream, audio stream. So for example, here I'm reporting on the right a claim and the evidence that is needed over Wikipedia in order to say that this claim is correct or false, right? So you may need some cells coming from a table in a page, and you may need another sentence coming from some text in another page of Wikipedia. Just a second. And so all these, of course, it's the entire Wikipedia. So you start from here, you need to find the pieces that are relevant in order to take a decision. It's not trivial. And so given a claim and a data collection, such as your Wikipedia corpus, you want to find the relevant objects, such as pages. And then within the pages, you want to find the text snippets or the cell values in a table to take the decision. Okay, please.
So you rely on Wikipedia to provide the actual facts that others Wikipedia.
So these facts at the top, they are manually written by an army of people paid by Amazon to create a data set. See, I will mention this in a moment. So this is the creation of the annotated data is coming from people who sat down and did it. But of course, there are some details here. So some of these claims that they manually wrote, I mean, there is a NIPS paper that I'm going to cite later about the dataset creation, and it's people basically creating multiple labels, supported, false, not enough evidence for claims with respect to Wikipedia. And I will get a bit more details in a moment. So again, you see the problem here. It's an information retrieval problem, and there is the first data set that has been published for this problem is 2018. And again, there are many solutions. Some of them are unsupervised, some of them are supervised. And you can imagine state-of-the-art comes from a pre-trained language model, you do the fine-tuning, etc., etc. Okay. So let's get to the main topic for today, which is this automatic verification. So we try to find all the evidence that is relevant. Now we are ready to, okay, we need to say this is true or false, okay? So I'm trying to stress here that the immediate goal for people working in this field is to create tools that can present the evidence, possibly the reasoning, we'll go back to this, and the conclusion for the input claim before the human fact checker writes the article. So I'm not trying to sell you the story that, you know, we're trying to do this completely automatic. We don't need a human, you know, I'm not trying to oversell this. But on the contrary, I believe that on the short term, this is the best we can do. On the medium term, maybe we can try to monitor and try to suggest the claim and we know with some evidence, but we are not there yet. Sorry, there was a question.
Yeah, so how do you limit claims that are a bit softer? So something is very effective, and the data said, okay, we have a thing that is anonymized.
We'll go to that. Great point. Great point. Yeah, and there are tons of methods, like my Scholar recommendation every day gives me 10 papers about fact-checking, how to do this. So, of course, I'm not going to tell you about all the possible methods, but I want to give you a feeling about what's going on. So there are some, I would like to divide this into not explainable and explainable, because it's important for what we do next. So the not explainable one, I'm going to give you an example next, but basically at the high level, the idea is that we would like to be as general as possible and possibly robust to noise in the data. So we would like to be able to handle any claim, and we would like to be able to do this even with data that it's noisy, right? So these black box method, they're better at this than the other methods. They are not there yet. We will see in a moment. Of course, the minus is that you just get a label as output because they are black box. Okay, you're using deep learning. You can try to use some of the methods for understanding what's going on in deep learning, but it's not really something for everybody. On the other hand, there are some explainable methods. So the plus is that they are very good at giving you clear evidence of what has been used to support and refute. That's the goal. But they make stricter assumptions on the claim and the data. Okay, so there are trade-offs here. So for the first black box verification, it looks like what we have been discussing so far, right? So you have a claim coming, you have some corpus that you trust. It can be containing table, text, images, but I'm going to focus on this data set for today, where you get Wikipedia with text and tables, okay? So you try to find all the evidence that is relevant. You get some sentences, you get some tables, you try to find the cells that are relevant for this. And then guess what? You dump all of these on a model. It's a pre-trained language model with fine-tuning that tries to come up with a label. Okay, there's a classifier at the end. And so you gather the evidence. The classifier can say true, false, not enough evidence. They try to be generic. And of course, the coverage here really depends on the amount of training data that you have. Because if you have training data that is able to cover only simple claims, we're going to cover that. But then maybe you start to put more complex claim that involve also relational data, and the model will learn eventually, okay, and can cover more. And then you may start arguing, okay, what about aggregates? Like, is the model, the BERT, able to understand how to do aggregates? And people are working on, okay, let's throw aggregates at BERT. How can we do this? And, and slowly people are pushing to make this as general as possible. Okay, and the good thing here is that it is robust enough to possible mistakes in this step. So if you're missing a little bit of evidence or you're bringing the wrong evidence, they still work to some extent. Okay, so let me go back for a moment to the example, right? So there is this data set that if you ever jump on this problem, I recommend you to read because they really spent a lot of effort and time trying to do it right. So they pay people to create sentences starting from Wikipedia pages, possibly more than one page, and they ask them to annotate. Okay, so they do this with multiple people from the same claim in order to get some consistency. The quality of the data set is not perfect. We keep finding errors, but still, it's a very good starting point because now you know that to verify this claim, you need to look at a certain table, certain cells, and certain sentences. And if you have all this evidence, a human is able to say, this is true, this is false, or the evidence is not enough. Okay? And I want to stress here that there are still strong assumptions. I'm going to distinguish the assumptions about the claim and the sources for the data. So you see that we are trying to be general, but you see that it's a very factual sentence, right? There is no ambiguity, and it's well formed. It's very different from a tweet, for example. Okay, there are no opinions, so there is no mix of opinion and facts. So it is important to keep in mind. So that's what's happening in this data set. And we are under the hypothesis that this source is of high quality, and we can rely on it to take a decision. Okay, so this is something that we're going to assume over and over. And my personal opinion is that Wikipedia, it's really a bit cheating because in Wikipedia, it's really high quality. It's really, it's a level of quality that you will never find in any other corpus because it is curated by people, as you know, and people are, careful in being consistent, such as that you see Lewis B pattern, Lewis B pattern, it is really ideal, right? You are removing a lot of problem about trying to put together things that are heterogeneous. But still, it's super challenging. Indeed, there is a competition around this data set. And we competed. We were 5 over 15 groups. And as you can see, we are not there yet in terms of results. So let me just precise a couple of keywords for people who are not familiar with the information retrieval. So here on the right, we have the precision and recall of getting the evidence. And you see that precision is basically every time you say something, how many times you are correct. Okay, so if you see 13%, it means that over 100 pieces of evidence, only 13 were correct. And the recall is, given that we know the ground truth, we know how many cells and sentences are needed, how many of them are you getting right? Okay, and then you can combine this in a metric, and you see that it is challenging. Okay, so we tried hard. So we are the best in terms of F1, which is the aggregation, but still, this is very low, right? 20% only. And then you need to verify, right? And this is the accuracy of the classifier. And you see that the best team was getting 57% in giving the label true, false, not enough information. So even with the assumptions that I gave you, even with people pushing this, I mean, this is a startup in Paris, and their job, their product is doing this. Okay, so there is still a lot of room, okay, for this black box method. And what else? And then, okay, there is a score they computed based on the combination of these, but that it doesn't matter. Okay, so you may be a bit, discouraged, but remember that I'm not trying to tell you that, this is working and we're gonna get 99% and we can do this automatically. The short-term goal is to create tools that are useful. And I'm gonna try to make this point in a bit. So far, so good? Yes.
So the five methods that are different, the way that they solve is
good point. Excellent. So they all start from the basic model that is given by these guys. They gave a baseline. So I didn't report the baseline model, but it's down in the ranking, and then people built on top of that. So for example, we for a matter of time and energy, we look only at the evidence retrieval. We didn't work on the classifier. Some people work on both, and there are many different methods with the papers describing them. Okay, so I'm going to move on because we have a lot to cover. So let's try to be a bit more specific. Now that you know the big picture, I hope you got a feeling. So what are we trying to do today? So today we focus on, given some textual content and some reference data, we want to assess if it's true or false and explain why. Okay, so just to remind you, we're not trying to match claims. To identify the check worthiness, okay? I'm not gonna talk now about matching claims to existing. We're not modeling the trust of the sources. We're not gonna talk about the network solutions. There is a very nice tutorial from 3 years ago about the graph algorithms that you can use for the network to model these problems, okay? And what I want to stress is that we are really interested in creating methods that people can understand what's going on, okay? So we're interested in the why. Indeed, we would like methods that are effective, good accuracy, they are scalable, they can handle a lot of claims, and are interpretable. Because, I'm personally under the assumption that if you don't give a good explanation about what's going on, it is completely useless, okay? Or in most cases, it's not useful because people, journalists or even target users, they will never just believe the label. They want to know why, okay? So today, I'm gonna dig a bit into two approaches in order to be able to do this verification with explanations. And to be a little bit more precise, we want to create functions such as, given a textual claim, some structured data, we want the label, confidence value, and some kind of explanation in the form of a description of the subset of the data that implies the decision. Okay, and depending on the system, this will change a little bit. Okay, so today I'm gonna cover two kinds of claims, and you will see what are the difference in a moment. I'm gonna start with the property claims. Okay, so those are the simplest claim ever, and they look like this. Imagine that you have an input textual claim saying that Elon Musk is the founder of Chevrolet. Okay, so any black box method, as the one that I mentioned earlier, any of them, I haven't tried, but I'm pretty sure that they will tell you it is false, right? Because there is plenty of evidence that, these two things are not related. So there is not a fact saying somewhere is not the founder of Chevrolet, right? But there is a lot of evidence that these two things are disconnected or not related, unrelated completely. So getting that it's false is quite easy, but getting an explanation is more tricky. So we came up with a system that will tell you that it is false because Chevrolet was founded in 1911 and Elon Musk was born in 1971. Okay, so we argue that it is better than the black boxes because this is an explanation that you can consume and contains the concept of person, company, birth year, founding year, and logical contradiction. Okay, so this case, it's easy because there is a very strong logical contradiction, but we're also interested in more subtle things, like this guy, Michael White. This claim is stating that he got his alma mater, his diploma, his degree, from UT Austin. Okay, and maybe it is something that it's a bit harder because maybe in our reference information, we don't have this fact that Michael White got his alma mater in UT Austin, but we have other facts. So our system in this case will say that I believe is false because this guy works at UT Austin, and in the US, it's a bit rare that you work in the place where you got your diploma. So there is a soft signal, right? It's not a strong contradiction. And there's another signal that he already has two alma mater listed for this guy in our corpus of information. Okay, so he has an alma mater from two places that are different from UT Austin. So given all these signals, I believe that it's more likely that it's false rather than true. Okay, so how do we do this? So now we're gonna exploit some of the things that we have seen during the week. So first of all, we are doing this little NLP task, which is of going from a piece of text, so the sentence, into something that is structured. Okay, so we have a little model that is based on decades of NLP for this problem, and it goes into a triple, and you may remember this from yesterday, where we have a predicate and a subject and an object. Okay, so in this case, we say alma mater, Michael White, UT Austin. So this is going to be our input for the verification. And then we assume that we have an incomplete knowledge graph that we mostly trust. Okay, so Yago, it's a popular generic knowledge graph. They did a verification. They claim that it's 95% accurate. Okay, so let's believe Fabian and let's use Yago, and let's say that it's good enough for this task. Okay, so I think that you guys have been watching a lot you have been exposed to knowledge graph a lot yesterday, but just to remind you, this is a graph, and we have some of these knowledge graphs that are freely available, such as the Yago I mentioned, DBpedia, or Wikidata. There are many of those, and there are many of those also that are in the enterprise. Okay, there are companies with their own knowledge graph, but I think that Diego already told you all the things, all the things you need to know. And just to remind you, we're going to use triples. So we are in the RDF model. I'm not going to talk much about the ontologies here because I'm not specifying them, but it's important to remind I'm using this whole table because I like the fact that it shows that these different knowledge bases out there, they're very rich in something that is very important for my method, which is the fact that they have a lot of types, thousands of types, and thousands of relation types, entity types and relation types. They're very rich, which means they're very rich semantically. Okay, so the people behind this, you know, in a crowd effort, or investing money from Google, they create schemas that are very, very rich. And it is important for what we're going to do. Okay, so, and of course, they're also big in terms of entities, right? I mean, we're talking about half a billion. It is from ages, I mean, long time ago, now they're much bigger. Okay. So something that is worth mentioning is that we are assuming in this setting that the sources are available. We mostly trust them, and they are rich in terms of these entities, type, and relations. Okay, but of course they are incomplete. So as Diego stressed yesterday, nobody will ever claim that a knowledge graph that tries to model the world is complete. So we are in what is called the open world assumption. Okay, so why is it so important for us? Because if I say Elon Musk is the founder of Chevrolet, I go and try to use the knowledge graph to do a lookup of this triple, the most naive solution, right? And it's not there. Can I say that it's not there because it's false or because it's just missing? it's hard. So that's the problem we are trying to solve. Okay. So those are the problem with the claims that are not in the knowledge graph. If I say, Bordeaux is in France, I can do the lookup, the triple is there, good. It's not very challenging. So far, so good, guys? Makes sense? Okay. So there's of course a lot of literature on how to do this. Some solutions are based on embeddings. So I don't have the time to go into this, but it is again related to these solutions coming from NLP. It is a bit older than BERT. And basically here, the idea is that for every word, you can get a representation in a low-dimensional vector space for every word, like the story of the cat. And then you have all these words that are in a certain space. So you can use the geometric properties to do comparison and say, okay, how likely it is that, Elon Musk is really the founder of Chevrolet. You can look at some geometric properties and say true or false. Okay. So those are based on embeddings. I'm not going to talk about this, but if you have time, I encourage you to read about this. It's very nice. And then there are other methods that try to exploit the structure and the information that is in the knowledge graph more explicitly. So they try to use the topological structure, and we try to find the path in order to say, okay, these things are likely to be related or not. Okay, so our solution is closer to these baselines. Good. Okay. Yes.
So I guess that one of the techniques is that should be used to identify how fundamental the fact is. Say that Paris is informed for one wants to you identify that these are major sources, major entities in the web. You say, okay, if it was true, it is likely that I would have evidence for that. If it is rare, then it is more likely that it may be missing from my interpretation. So it's true that the knowledge graphs have incomplete information. But some information is more likely to be missing than others. If you see some fundamental fact, and you identify this is a fundamental, I mean, this is, I think, what we do as humans. If this was true, I would see it there.
I agree with you. And I see your point. So I think that the default answer will be popularity is important. We don't model it explicitly. Let's let the model learn about this, right? But if you want to use something more declarative as we are trying to do, yes, this is something that should be considered. But as far as I know, no, wait, I believe that there are people that have exploited this intuition. I don't have really a reference for you, but I believe that there is someone looking at the fact that it's a valid intuition, right? And I think that people looking at, declarative solutions using paths, they model somehow this popularity feature. In our work, we don't do this. I'm not going to talk about this, but it makes sense. Yes, please.
General, is it like a static analysis in the knowledge graph, or there are models where you can update your knowledge graph according to whenever you get a wrong answer or not?
So there is a paper in the LDB a few years ago where they try to model what is true and what is false explicitly in a knowledge graph. So they also add facts about things that are false. So maybe it goes a little bit into this direction. But I'm not sure I got your point. So you say that maybe we should extend the knowledge in order to have also explicitly the false facts. Is that what you are suggesting?
Yeah, maybe I'm thinking like then what you're getting like a string of questions maybe. So after a question that you can know true or false to update your knowledge graph, if there's any setting in this way.
I think that paper goes in that direction, and it's from Cornell and Google. I don't have it in the references, but I can add it. And it's about having this, they call it anti-knowledge graph, where they also model false facts. But I will have to dig into the details to give you a better answer, because I just remember the intuition about it. Yes?
The triple extraction process.
Yes.
Predicate's name, something fixed. Is there a fixed vocabulary, or is it something that the language comes up with?
Good point. So we have been trying different things, and in the end, we found that leaving it a bit open-ended is the best solution. And then you have a little matching task between the predicate that you extract and the predicates that are in the dictionary, because the number of predicates is too big to do a classifier. So we prefer to go with this matching approach. Okay, great, great, great. So we're getting there. So what do we do? And okay, yeah, we still have time. Okay, so let's go back to the Michael White example, right? So I was telling you that, okay, in this case, you know, we would like to be able to use the evidence and there is no information that he works at UT Austin, but we believe from our model that we should expose some evidence that we believe this is the evidence that justify the fact that we say that it's false. Okay, so the triples about the fact that he works in this university and the fact that he has an alma mater. But maybe, you know, there are thousands, hundreds of triples about this guy. So why those are the triples that are important? That's the challenge, right? I mean, how do we come up with this? And here we go back to some of the things that you guys know, because we are exploiting something that is basically approximate rules. So I believe that Benny talked a bit about approximate rules in relational data. Those are approximate rules over the knowledge graph. Okay, and how do they look? They look a bit like denial constraints. I've been working on denial constraints for relational data for some time, and I thought maybe we can use this also over graphs. And they look like this. You have the atoms that are the predicates with the universal variables, and you are saying, okay, it cannot be the case. There is a contradiction if someone has more than one alma mater. Of course, there is a very soft constraint in the sense that it's possible to have two alma mater, but you know, there is a certain probability. It is the support of the rule that we're going to use as a proxy for the probability that says that, you know, if this is not something, I mean, it may be a signal that something is wrong. Okay, that if you can instantiate this, maybe one of the two triples is incorrect. Another example is if you work in the place where you got the alma mater, right? If you find this pattern for a certain X and Y, then it's likely to be a contradiction with a certain probability. Okay, so the question now is, okay, this seems cool, right? I mean, we can use rules to gather the evidence that justify. So the next question is, okay, how do you get these rules, right? And I think that Floris is going to talk a little bit about this afternoon, but there are tools for relational data and for graph data that try to mine the rules directly from the graph. Okay, so it is totally unsupervised. You take your structural data, you start counting basically, and you find patterns and you say, okay, given all this evidence, I believe there is a rule. There is a pointer to one paper that tries to mine these negative rules. Okay, so how do they look? I think that you guys are already able to read it, but just in case, this is the rule for the founding of the company, right? So the founding year for the company, the birth year for a person, we are stating that this person is the founder, and we are comparing the years, right? If this rule can be instantiated over the atoms, the facts, the triples coming from the knowledge graph, and the triple that is the claim that is given. So we start from the claim is founder Chevrolet Elon Musk. So if we try to instantiate this rule, basically we know the X Chevrolet, Musk, so we query the knowledge base to see if we have founding year and birth year. If this trigger, we know that at least one triple among them is incorrect, right? Remember our little assumption that we believe that those are likely to be correct. So we believe, you know, we have evidence that this strong rule is telling us that the founder cannot be Elon Musk. Okay? Yes?
How do you extract from, say, like entities and relations? Because you're coming from a natural language text, and how do you extract entities and relations accurately from the natural language? And how do you build this like a correspondence, say the predicates to the knowledge graph?
Yes, I see. So, of course, all of this is structured and it's already in the knowledge graph. So I'm not building the knowledge graph. So your point is how reliable is going from the sentence to the triple, right? It's not super reliable. I would say that it's between 70 and 80%. And it depends a lot on the structure of the sentence. So if the sentence is factual, one fact, yes, we can do it with more than 90%. If it is like, you know, Paolo was born in Rome and then he moved to US, the numbers go down. And I'm happy to talk more about the model, but it's not really central for us. I mean, it is a traditional task for creating triples from text. And there are many methods. Yes?
How do you decide which rules are potentially useful and relevant? Because you could combine...
We're going to be there in a moment. Excellent point, because we are excellent. Hold on a few minutes and we get there, because we're going to take them all, and you will see how we combine them in a moment. There was another question? Sure.
Trying to summarize the paper, and then when you write code, maybe to
I can summarize what? Sorry.
To improve when you want to perform the sentence in words. Maybe summarize.
The sentence, you mean?
Yes.
I don't know. I mean, text summarization is a beast that I never touched deeply, so I don't know what is going to happen, to be honest. But because, you know, text summarization is going to try to find the silent facts in a way, maybe. So maybe, I mean, the intuition is good, but I don't have an answer. Sorry. I think it's a valid point, but then you're going to miss. I mean, you're going to move some facts. So what about if the facts that are false are the ones you're removing? So it's not straightforward to me, but it's a nice intuition. Okay. So these negative roots, is something that we use to identify inconsistencies. This is a simple case with one rule, right? We're going to talk in a moment about cases with multiple rules that can be involving the atom founder. So you may have multiple rules that are triggering, and some of them can even be contradictory, right? So we're going to talk about this because we have negative roots, and there are a bunch of them, just to give you a feeling of the beauty of having the knowledge base with all these predicates, right? I mean, we can mine roots saying that the president of the United States must be born in the US, right? It's a rule that we found with support 1, or you cannot be married to your child. And you may be surprised about it 0.9, but it is coming from the fact that in Iago and Freebase, there are in Egypt people that were married their children, right? And there are, you know, fictional characters. So there is a little bit of noise that brings this a little bit down, okay? But of course, this exercise of mining rules is something that has been done for a long time, but not really with emphasis on these inconsistencies, but more on trying to address the missing data in the knowledge graph. And this is something that, you know, there is a very seminal work from 2013, but this has been done for a very long time in knowledge representation. I'm sure that Diego and others can probably point to this mining done with other methods for a long time. For knowledge bases, something that has been done more recently is really to create a system that can produce thousands of rules like this. If you have a child in common with someone, so Paolo, Mary, they have a child in common in the triples in the knowledge base, you can derive that they are likely to be married. Okay, so we also have these rules in the mix because those are important to address the fact that the knowledge base is incomplete. Okay, so maybe, you know, the fact is true and that is given that Paolo and Mary are married, the triple is not there, but I have this information, so it is bringing evidence that spouse is indeed true, okay? So the way that we use these negative rules is that actually we don't model them using the bottom, but we move founder to the right-hand side. So in our rules, we have some rules implying founder and some rules implying neg founder, okay? And then we have a constraint saying that founder and neg founder cannot be true at the same time, okay? So okay, we have a lot of rules. I'm gonna skip this. I just want to mention that we have 20,000 rules that we collected over knowledge graph over time, and we put them in a website. So if you ever need logical rules for your knowledge base, we have them with the support, and for a few hundreds of them, we also have the human confidence that we computed by testing the triples. If you're interested, we have a paper on this. I think it's cool stuff because these rules, they can be used for this problem, but they can be used for query optimization. They can be used for many things. Okay. So I'm ready to get to the system to tell you the full story about this. So I'm not going to talk today about the role of the web. This is not important. This is something that we did a few years ago with people at Arizona State University. And we start from creating the claim C. So we get this triple, and we assume that we have the knowledge graph as input, and the output of the system is the assessment that it's more likely to be true or false with a certain explanation that is the list of rules that has been triggered with the evidence used. Okay, so here to start, you can either think of this in a pay-as-you-go fashion, where basically you mine the rule for the given predicate, or you can just do a lookup over this rule hub that I mentioned. You can just go here and say, okay, give me all the rules for a spouse, right, or for founder. So now we have we can gather the rules and the evidence from the knowledge graph. So given the input claim founder, I'm going to try to instantiate the rule, and I will find some of the facts over the knowledge graph. So now I'm going to push this information to a second phase where we have a reasoner. So why we have a reasoner? Because in this example, one rule, strong evidence, and if you imagine that I have neg founder on the right here, and I have only evidence that neg founder is true. But in some cases, you may have a lot of rules that are triggered, like the case of Michael White. So in that case, we cannot simply just take a decision, but we need to reason about these rules and how they combine. And in order to decide just if it is more likely to be founder or neg founder, which one has a higher probability. Okay, so here we use the most probable stable model of these weighted rules. So we exploit some work on from the colleague at the ASU, and we have a reasoner that takes all these rules with their confidence. We take the facts with their confidence. I'm not stressing this, but we have facts that we trust more from the knowledge base, trust the fact that we trust less from the web, and then we let the reasoner try to come up with the probability of founder being true or neg founder being true. Then we compare this probability. The one that is higher wins, and it's the one that we give as the output. There was one question.
So my question is whether you can contain some more elaborated things like the arithmetic or I don't know, text analysis or something that you know.
Let me think a second. So to be honest, I never pushed much in that direction because we were not able to mine more complex rules. So I was very biased in this by the fact that what can we mine, and we already do a lot of tricks and heuristics in order to mine also comparison across literal values. That is something that requires, your search space grows a lot. So we have a lot of tricks in the mining. Having more complex predicates, I think is doable. I never thought about this, but it will increase even more the search space, right? So things like aggregates, I will exclude it, of course, but maybe more, as long as they are binary comparison, I think it's doable, right? Yeah, probably it's going to be even more expensive, right? Because you're going to do in the mining a lot of tests, but it may work as long as it's binary. Yeah. Yes.
Is the way to compute the probability of the rules and then use it to the pipeline is affected by the syntax, or is it
the syntax? I mean,
fuzzy logic, the syntax of the rule, determining how we compute probability score depending on.
I think that in the reasoner that we are using, there is no such property. So, but yeah, that's what I know from the rewriting of that we are doing from our rules, the rules consumed by the reasoner in this case. Okay, so this is one way to look at the problem, and as you can imagine, there are many other baselines, right? I mean, you can do this with a classifier, with the embeddings, and many other ways. So, of course, we run experiments, and by using DBpedia predicates, where we created the true and false claims, then we remove the true claims from the data. We measure precision recall F measure, and we have some baselines using link prediction in knowledge graph and text mining, and also using the rules without the weights to compare to see the importance of the weighted rules and the reasoner. Okay, so I'm not going to spend much time on the numbers because it's not important to me. What I would just to say is that there are many ways. Some of those may be better than us in some predicates. So I'm not really obsessed about the quality, which is comparable, let's say. What is important to me is to argue that we need to push for methods that are able to tell you, I believe this is edge you should add to your knowledge base, so that the fact is true because of this justification, because of this evidence. Okay, so the rule acts as the explanation for the decision we are taking. Okay, does it make sense to everybody? Any other comment?
How you created the full stack? Did you say that things that assume you satisfy functional dependency and you created?
You mean here the false fact? Oops, I cannot see this. The false fact here. To be honest, I don't remember right now. I suspect that what we did was trying to. So let's say that you have the predicate spouse. So you know that it's person and person. So you take one guy and you take another guy and say that they are married. I will have to double check, but because maybe it's a bit more sophisticated, but along these lines. So we're just enforcing the types. Okay. Yeah, sorry.
I have a silly question. I mean, suppose you want to do fact checking and there are fact checkers websites. Are you allowed to do so to check your own fact? Or should we dispute that? Because, I mean, otherwise people can start making fake fact checking thing and say that it's a fact check. And so then you postpone, I mean, you're ending up in the same situation.
Sorry, you are going back to the claim review proposition, the fact that you put the information online. Is that the? Yeah. So for this claim review, I didn't get into the details, but of course, Google, I mean, we tried this. So we have a service that I'm going to introduce in a moment where we produce labels for new claims. And we try to create claim reviews. We created them. We checked that Google was seeing them, but Google was not using it in the results. So there is a filtering mechanism. I guess that they have a white list of the sites that they trust.
2 years ago, we did a workshop on identifying fake.
All right. There's another question over there.
For instance, I'm somebody who wants to generate a statement. So my work would now be to come up with a formula that is consistent with your. So are there lower bound analysis, like I need at least this much computational power to do that?
Absolutely. I mean, are you saying that people can use any algorithm that is published in order to create adversarial cases, or to cover themselves? Sure, it's definitely possible.
But maybe if it's harder in the sense that to come up with the formula, you need at least XP time or something like that.
I see. So what is your question? Sorry, I didn't get it.
Analysis to say, okay, this is the power of the logic that you have. Then the adversary needs at least this much power to break the system.
I see. Yeah, that's a way to look at this, I guess. Yeah, but I mean, this goes back, I guess, to the whole problem of, should people publish solutions? I guess there is a hidden, I mean, in your comment, the bigger question of, if you publish the solution, people can always try to play with this, right? Yeah. Okay, so I think that we are more or less on time. I would like to switch to the second topic about these statistical claims. Okay, so I'm assuming that you got a feeling about, okay, we can use mining of rules, these rules, we can use them somehow that, as long as I map my text to some structured data, rules can be useful, right, for these simple claims. But unfortunately, these simple claims are part of the claims out there, but it's a small part, right? I mean, there's a long tail of possible claims with different shapes and forms. So another kind of claim that is a bit more challenging is what we call statistical claims. Okay, so how do they look? So it's exactly the same setting, and they will look like this. Imagine that you have a tweet from someone in the middle of the pandemic in 2020 saying, the US death rate is not 3.4, it's 1.3 and falling because, I'm a friend of Trump and I believe that social distancing is useless, blah, 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 right? So there is a strong statement here, right? I mean, the US death rate, as a matter of fact, is this, is not that, right? So imagine that we have this little table here on the right, very simplistic, but it is telling us, on March 20 in 2020, this is saying that, those are the number of cases and deaths. I mean, it is totally toy and made up just to make the point, right? So you can use this data and compute the death rate if you define the death rate as the number of deaths of the number of cases. Now, you can say, okay, I can verify this, but with the approach that we just discussed, if we translate it to relational data, you can definitely mine some approximate constraints of relational data. Absolutely, we did it, it works, it's useful to some extent for data cleaning, but if you're doing this exercise, the rules that you mine, they're going to build things like functional dependency and denial constraints. For example, this is the key, is the functional dependency that implies deaths and cases. And, there is a little denial constraints telling you that the death number, it's always smaller than the case number. Done. We have our set of rules. So you see that you can verify a claim like if I say the number of cases in Italy, it's smaller than the number of deaths. You can take what we just saw with explain and it will work, right? Because there is a rule that contradicts that claim. But you see that in this case, we cover just a few claims that are not very interesting, but there are more interesting claims, right? So you see that we are stepping up the challenge to something that is not covered by the rules, definitely. Okay, and also because the schema is less rich in terms of predicates, etc. So how do we handle these complex cases where we also have the mathematical operations that I mean they are simple, but still they require us to combine values, right? So we have the right values. So this is something that we did with a system. It's called Corona Check. I wanted to do a demo, but I think that I'm going to skip it for the sake of time. It's online, so feel free to break it. I mean, it's very easy to break. You can easily find the claims that will fail. But the idea is that it's a system in many languages, and we also have an API that is used by a couple of fact-checking organizations that, given a statistical claim, will give you the label. This cannot be missing, but also the evidence that has been used to verify it. So basically, what is happening behind is that we are deriving a query, and then we show people, fact checkers or users, if you go online, the fact that, okay, we understood that we need to use this formula, and it's giving us a certain value, because I'm using A divided B, I'm going over the total number of deaths, I'm going over the total number of confirmed, I'm using the attribute March, I'm using the raw value USA, and this is the value that I get in that cell. Okay, so we're basically unwrapping the query and telling them, given this evidence, given this operation, I get 2.8, 2.8, which is different from 1.3, so we believe it's false. Okay, so this has been online for quite some time, and we had more than 20,000 people using it. So we have quite some experience on this. And how do we do this, right? So the problem formulation is the following. Assume that again, we have someone giving us some reliable data. Now we can get into a debate, about the number of cases, and it's, you're right, it's a delicate point, but assume that you have some data that it's the best you can get, right? And there is a service since 2020 from a university in the US that every day gives you the data, and it's there and everybody can use it, okay? So this is our set of relational tables that we trust, D. And then we say that a claim, we try to model it as basically the following query. We say that it describes a comparison operation, OP, greater than, equal, less than, between the value of a query and a certain parameter P when Q is executed on D. So the claim is correct if there exists at least one query, D, that with the right operation and P for it that evaluates to true. So if we're able to represent the claim as a query that is true over the data, we say, okay, it seems that this is true. Okay, so then there are cases that are a bit simpler, like the number of new cases increased by 100% in March in France. You see, this 100% is the P that we're after, so we call them explicit claims, but there are some of them that are more difficult, like the comment that someone made earlier, like the number of deaths increased in March in France, or the number of deaths increased a lot in March. So those are more challenging, and we call them the general claims because the P is not explicit. Okay, so if there is no query such that this evaluates to true, then we say that the claim is false. Now there is a big jump from what we did earlier and what we're doing now, and I hope that you see this, because earlier we were in the open world assumption, while here we are definitely exploiting the closed world assumption, right? If there is no solution, this is the entire reality, we have everything. If there is no solution that says that something is true, it must be false. Okay, so closed world assumption. And again, I like to stress that we have assumptions, the data is available and is something that we can trust. And we have also assumptions over the structure of the claim, of course, right? I mean, it is not going to work for every possible claim. There are claims that doesn't capture. And of course, there are some challenges, right? Because you can imagine that the number of possible queries is big, and it's possible to have some matches that are spurious, that just by chance. So going back to this example, if I try to generate all the possible queries in order to verify that, there is one of them giving 1.3, I can do lookup. Okay, none of them contains 1.3 or 0.013, right? But I can also compute ratios and keep going with different formulas. And eventually you see that I found a 1.3 coming from 130 divided by 100, but it has nothing to do with the sentence, right? It is completely brute force trying to find all the possible sentences. And by chance, I found a match because we're not using the meaning of this. We're not trying to translate it, right? So it's clear that in order to restrict the space and to find meaningful things, we need to avoid these spurious matches. We need to try to understand the language. So how do we do this? How do we go from the claim to a SQL query? Yes. Yeah. I mean, I wanted to make the point that if you try not to use the text, you are, in a huge space and you can find things by chance. Exactly. So we want to understand, I wanted to motivate the fact that we need really to look at the NLP part here, right? So what did we do? So this is a claim in text. So we have a leader classifier saying, it is a statistical claim or not. In case it is not statistical, we drop it. We don't even try. Like people, the day that we launch it, we had people looking for things like garlic cures coronavirus. And we were giving them answers like, yes, the percentage of, because we were not able to understand what was going on, right? So we have a leader classifier saying, Okay, just, you know, numerical stuff, statistical stuff. Then if the P is there, we try to identify it and we pass it to the next step. But here we have the layer where we try to understand the language, right? And guess what? This is based on pre-trained language models. This XLM is from Facebook. It's very cool because it's trained on multiple languages. So when you use Corona Check in French, in English, or in Chinese, it's the same model underlying, okay? So we train the same classifiers. We derive 4 different classifiers for each component of the query. Then we have a query templates, and we try to fill the slots in the query templates with the pieces that are coming from the classifier. That's a standard way to go from text to queries. There are other approaches. This is a very simple approach that works in our case. Yes. Great. I completely agree. Let's get there later, because ambiguity is my passion this year. So I can talk about ambiguity for hours, but I keep it for the end. So yes, so that rate is ambiguous, but let's assume that in this case, we are happy with one interpretation of that rate, which is number of cases of a number of deaths. So what the classifiers are going to do is that, okay, I take these as input. I'm not going to tell you how we bootstrap the classifier, so you can find it in the paper. It's a nice exercise because we didn't have data for training, so we created it in a certain way. But let's say that we got decent classifiers for these different 4 pieces of the data, right? So we are able to predict the relation, and of course, this is not going to be perfect, right? There can be errors, but in this case, we put at the top total deaths, total confirmed. We are trying to predict the attributes that are relevant, the keys, the key values, so to identify the tuples, and the formula. So now we have all these elements coming together, and what we do is that we take the top K predictions, we put them in the templates, and we try. Okay, so in most experiments, we use top 3, top 5, we try all the possible combinations. If there is no query, it's going to be false. Okay, and because we are going to check if the query that we generate it's close to the value coming from P. Okay, so a few comments. In Corona Check, if you try, you don't get these top 3, top 4, you just get the top 1. It's a bit simplified. Another important comment is that many things can go wrong. Many things, you know. So you can break it very easily because you can try things like this. Yesterday, the number of new cases in France decreased a lot, right? So you can imagine our leader classifiers, they're gonna identify that you need a certain table, you need a certain attribute, key, formula, but P here, it's really domain specific, dataset specific. So there is no magic meaning that I can give to a lot, even if I, somehow know, and this is something that when you go to some other kind of data, the temperature increased a lot in Italy in the last 10 years is different from the number of cases increased a lot, right? So it is really domain specific. So it's very complicated. And another complicated case is that people, unfortunately, they have this problem that they try to test things that we don't have in our data. So for example, we have the data with Italy, Japan, France, and people keep writing things like in Europe, the number of new cases is decreasing this month. So new confirmed, time, I was able to manage the formula, and I understand that, just decreasing, it means that I need a 0, great. But I mean, Europe is not there, right? So I need to learn that when they say Europe, I need to combine multiple countries, and then Southern Europe, Western Europe. So what we do in this case is that we try to fail early and ask people, will you be so kind to tell me what are the labels that I need in order to fix this, to answer this question, right? So we do this exercise of getting new training data from the users, and in the papers we show that with my great surprise, people are so kind to give real annotations, so we can train a model with their annotation, and it works. So we try to expand the understanding of the knowledge with the new labels. Okay, so far so good? Okay, I think we are on time. So what I've been describing, it's part of a bigger system. So I just told you a little bit about this, given a claim and the data sets, how to do the generation of the query. But this is actually something that we did in a rush in 2020 when we were submitting the paper, because there was this coronavirus with the cases and it was appealing. But it's part of a bigger system that is motivated by another scenario that I think it's worth sharing, because it shows that verification go beyond misinformation. So we started a project with the International Energy Agency in Paris. This is basically all the Western countries together trying to understand what to do in terms of energy, what is going to happen, climate change, et cetera, right? Reserves, should we buy oil, gas, what is happening? And every year, this organization writes a big book that goes on the desk of Macron and all the people making the big decisions, because they need to know what's going on in terms of energy, right? So they write this book that it looks a bit like this. And I'm trying to highlight all the claims that are in these 2 pages. Those are claims that are coming from the analysis that they do over the data. So what is the problem? They write the book and they need to verify what they write, right, before publishing. Also because the data can change a little bit, they have predictions over the future. So maybe someone said, wait, the prediction now is different. Here is the new version, like before releasing the book. So they need to verify. And there is a team of 4 people there doing this for months after the book is published, it's written. So, this big delay because they need to verify. So we told them, okay, let us try to help, right? So here we start in a setting where there is a big text. You see this little red, those are annotations about the claims that need to be verified, okay? So we are not doing the check worthiness. We didn't need to do that in Corona Check because I assumed that people were putting worth checking claims. But here we have this annotation, we have these statistical claims about, the biggest oil consumer, increase, numbers, et cetera, and we have the time series. Those are the data that is coming from them because they are the one collecting the data. Okay, so we assume that this is trustable, and we assume that we have the worth checking claims highlighted. And now it should be not surprising to you because it's going to happen the same exercise, right? We have the claim, we try to infer the relation, the attribute, primary key, and the formula. Okay, so what is the difference here? Corona Check was easy to build in a few weeks with Scrutinizer. Here, because we started from something much, much harder, which is the case like Diego explained yesterday, where you don't really control how these tables are written, and there are hundreds of them. So there is a lot of variety, and so the search space for these labels is much, much bigger compared to Corona Check. And the formulas, there are tons, a large number of formulas that can be quite complicated with multiple elements. And so the setting is a bit different, right? So it is harder, and because of this bigger challenge, but also we have a slightly different setting. We have a large number of claims in the batch, and we have access to a little crowd of checkers, okay? So basically, we are scaling what I told you about Corona Check up to build something bigger, because we have thousands of claims, multiple experts in the process, hundreds of data sets. So we need to create more training data. We need to have a smart way to interact with these people. So in the database literature, there is a lot of work about this crowdsourcing approach. And the idea in crowdsourcing is that you have some kind of problem that you want to solve. So basically, you go to this platform, you decompose this problem into smaller problems that one of the workers, one of the people can handle individually. Then you put together all the answers from the workers, and you create and you're able to output the solution. Okay, so there is a paradigm that is quite interesting because it opens a lot of questions about how to solve the problem, how you decompose it, what are the right questions to ask, which options to show, which order to use. So let me dig a little bit into the order because it's quite fascinating to me. We realize that when you have a classifier, there are some examples for which you are good, you have high confidence, some examples you have low confidence. So a basic intuition here is that you would like to help them, right? So you would like to show examples for which you have confidence. But on the other hand, you need also to learn, and you want to go after the corner cases to improve your training set and learn about the difficult cases. So how do you do this, right? Do you go after the interesting claims first, or you go after the claims that are easier to use? Because you want these people to help you, but also to get something out of it. And also, how do you order them with respect to the text structure, right? Because imagine that you're doing this exercise, and they ask you something that is coming from this paragraph about oil in France. And then I give you the next question about something about gas in Qatar. So you need to completely switch context. You need to read the entire paragraph. So there are also constraints coming from the fact that maybe I should try to give claims that are close to each other to a single person so that I minimize this context switch. So those are all considerations that are standard when you deal with the crowdsourcing. It applies also in this context. And I'm happy to share with you, as far as I know, the only study, user study, where we basically did the following experiments. The people in the institution, they were so nice to give access to the checkers. And we took these poor people and we put some of them into a bucket that we're using for a certain number of claims of increasing complexity. We give them the claims and the access to their usual tools, Access, Excel, whatever they wanted to use, in 20 minutes. And they were supposed to check as many claims as possible. So they were able to check 10, 13, 8, skipping 2, okay? And then we gave to 4 other people our tool, and we told them, try to verify these claims. So you see that the number of claims that they have been able to verify in the same amount of time, it's about the double. And of course, they skipped some, and they also made some mistakes, okay? I'm not too worried about the mistakes because the protocol there is that the 3 checkers check anyway every claim, so you can use simple things like majority voting. But the point is that there is some evidence that even if the tools that I've been showing you, they don't have perfect accuracy, they're useful to people, okay? And we showed also that the verification time in seconds for a claim doesn't increase too much with the complexity of the claim, or the complexity is basically measuring the number of relation, attributes, keys, and the complexity of the formula. Okay, so you see that for us, for the system and for the user, they were not able to get to the complex claims. And of course, in the paper, we have much more experiments about the full end-to-end automatic approach. We compare to many other papers also from the NLP community, that because the NLP community is not afraid of using tabular data in their models. So they have models to do fact-checking with tables. So we compare also against this thing. You can find them in the paper if you like. This makes sense to everybody? Okay. I also have some results over the crowd, but I think I'm gonna skip it in the rest in the interest of time, because I've been touching on this problem of involving users, and I want to mention that many efforts have been done in order to say, you know what? I mean, we have access to people. People are great in things like Wikipedia, right? We collectively gather evidence. You know, we do wonders, and maybe we can do the same for fact checking. So we can, throw these things and try to use the crowd in order to verify the claim itself, right? Just tell me, given your knowledge, given the things you can access, if it is true or false. And there are many initiatives. One I want to mention, it is coming from the guy who founded Wikipedia, and he closed very shortly after he launched. And most of these initiatives, they just fail for multiple reasons. The main reason is that, of course, there are advantages, scalability and faster response, but there is the risk of manipulation by people who are, with an interest. There is lower credibility in general. There can be human bias. There is imbalance in the way that people select these claims. Okay, so this crowdsourcing is something very interesting, but the only initiative that has some success is this Birdwatch on Twitter. So probably you never heard about this because it's only based in the US for now, but hopefully they won't stop it and it will come also to us. The idea is that they really want to do community-based fact-checking. They're trying to do it right. And the idea is that you see a tweet, and as a person involved in birdwatch, you can write a birdwatch note saying, I believe based on this page and this article in PubMed that this claim is incorrect, and you put some information, right? So you write as a fact checker a little debunking of what you saw, right? And then all the other people involved in birdwatch, they can rate what you are doing, like it's useful, yes or not, because there are high quality sources, easy to understand, etc., etc. Okay, so there is a two-step mechanism. People can fact check, people can give ratings, and this is a Twitter initiative. Now, we wanted to touch on this problem. So we did basically a study where we wanted to answer many questions. I reported the 3 questions, and maybe I will just skip a few things, but we wanted to, see, okay, how good are these people, evaluating through the crowd of birdwatch. And let me skip this for a second. So we did the following. We say, okay, we can look at this problem by saying that given a tweet, you have multiple ways to verify if something is false or true, right? So we talk about the experts, we talk about the automatic methods, but the crowd is just yet another method that ultimately will give you some label, right? And of course, we can compare them in terms of labels, in terms of evidence, and in terms of how they select the claims. Okay, they check worthiness, the evidence, etc. So basically, what I'm saying is that there is a tweet, there is maybe the crowd that is writing the note with all the metadata. So it is written by someone in the birdwatch program, and then there is for the same claim, maybe there is also a claim review done by one of the experts, right? And you can also run the automatic methods over this, right? Makes sense? There are multiple things, we can compare them. So what we did is that we said, okay, we really want to look into this. What is the right way? We said, okay, we know that the ground truth is going to be the claim review, the experts. So we just need to do the little exercise to match all the tweets that have been verified by the crowd against the claim reviews so that we have the ground truth, because we know that the ground truth is coming from these guys, right, from the claim reviews. So we can now compare apples with apples because it is about the same claim. So some poor people sat down for a few days trying to do annotations of this matching, right? I mean, I needed to match that the earthquake in Italy killed 10 people. Some bird watcher, Good Samaritan, did the check for this. So there is a tweet that has been checked by Birdwatch. And then I try to find in claim review if there is a claim review about the same event. And if the number is the same, okay, the Birdwatch guy is good. Otherwise, there is a mismatch. Okay, so we did it a bit ourselves, and a bit for the majority, we paid people. Of course, this is done by filtering, by using, guess what? Sentence BERT, which is a model based on BERT in order to do the text matching. So we filtered them. We created finally the tweets that are aligned between the claim reviews and the tweets that are being verified by the Birdwatch. So now we have stuff to analyze, okay? There is a little demo online on this. I'm gonna skip it in the interest of time. And I'm also gonna skip this stuff, but I want to mention this. So one analysis that we did that I think it's important is that we looked at the sources, right? And what we found is that it's possible to model the sources with respect to some API that tells you how good is a source according to this company run by journalists, okay? So they get a score. And what is interesting is that this score that is coming from the professional, it's our ground truth, and we compare it against the judgment of the quality of the source given by the users. And you see that for what the Birdwatch people say that it's high quality source, we have this distribution, right? And for what people say that we have low quality source, they are actually even better according to the journalists. So what's going on here? That there are some people in Birdwatch that when they see, for example, the New York Times saying that Trump lost the election, they say this is a bad source, right? So even Birdwatch, with all the money and the energy of Twitter, is still exposed to the fact that there are people with their agenda and they can somehow steer the algorithms. Okay. And finally, I just want to mention the main result, which basically is that on this side, we have the labels coming from claim review. And here at the top, we have the labels for Birdwatch, misleading, misinformation, not misleading. And in general, the trend is that they agree on their decisions. You see that we have not credible and tweets labeled as misleading. There is a very large intersection. So they tend to agree. So the crowd is, it's exposed to some problems, but in general, the power of the crowd is there, and it's possible to do verification that it's according to the experts. Okay? So I told you a few things, right? So maybe at this point, I can try to wrap up and mention if we are ready for adoption, right? I mean, we have a paper where we interviewed the fact checkers and we try to see, okay, are these things useful for you or not, right? And actually, we have more problems than good points because there are many, many things that are still not there, right? So at this point, I guess that you also see that there's definitely a problem of expressive power of the language, that we can handle some specific claims, but we are not able to handle complex claim or complex sentences with multiple claims. And something that we have been doing that maybe it's of interest here is that we worked with claims like this with the scrutinizer, but then we also found claims that are even more complex, for which the SQL query, it gets very, very big and almost impossible to predict. So what we did this year is that we have the first paper that tries to go from text to a fragment of data log. It's called temporal data log, in order to do this verification with more rich languages. And there are many initiatives, of course, in this direction. And someone mentioned the ambiguity. So the ambiguity, it's a huge problem. I've been working on this a lot. If you open Corona Check, you will find that given a claim, in most cases, we give alternative interpretation. Because, for example, if I say the number of cases is going up in Italy, is it today, this week, this month? It's not clear. And depending on the interpretation, you can have different labels. And that rate, it's a very good example, because you can interpret it as a mortality rate or fatality rate. Those are two different tables that you need to involve. So again, these assumptions are there, and we try to reduce them more and more. And it's open for a lot of contributions, I believe. Some people are also looking at the usability, given the label and the data that you collect, the sentences, how can you write a little piece that is like a decent debunk article? Okay, so this is cool. But I think that in terms of research direction, what I hope that some people maybe in the future will work on is how to drop some of the assumptions that we have, right? So automatic methods, they are poor with the difficult natural language text, such as the tweets. They are not able to match very well the claims with the claim review, but the crowd is good at this. But the crowd, on the other hand, it fails on complex claims where the experts are good. We know that the experts are slow and rely on few sources, while the crowd automatic methods scale. So it is not clear how to combine. I mean, we have all these methods that I try to present today, and it's not clear what is the right way to combine these in a unified solution. Nobody knows. And also consider the orthogonal challenge that we have many automatic methods that X that is good on a certain claim type, given some clean data, but this is all scattered over different pieces, and we are still far away from having a good collaborative solution. The naive way is to say, okay, I'm going to use automatic tools to do some real time, provide evidence. The platform users, the crowd, they do a first checking, and then I try to involve experts. Sure, But what is the right way to do this? I mean, assuming that we can model the trust of each actor and the cost, I think that there is room here to do a very nice modeling of a framework that tries to put all of this together. And I don't know how to do this because getting a good estimate of the trust and the cost is still an open question. And there are many other research directions that I'm not going to go into details because those are orthogonal to deep learning and NLP in general. Multi-language, bias in the models, this is a big topic. Multimodality, you have image and text together. So now you need to merge signals. Explainability, real time, we can go over and over. I'm going to use my last 5 minutes for the biggest challenge that is out there, because all the challenges that I've been telling you, I believe they are good and people should work on this, and I'm working on this, so I buy it. But I need to share with you that we have a bigger problem, and it's the fact that the human is involved in this. Here is a screenshot from Facebook. One guy, remember when I told you, you know, if you try to share something that is clearly false, they will try to tell you, maybe you want to look at this Nature paper before doing this. The guy is saying, do you really think I'm going to believe you after all my years of research on vaccines, right? You know, stop Facebook, give me a break. Or, you know, thank you, Facebook, for being so concerned. Do you really think I'm going to trust you? And my favorite is the guy giving tips on how to block fact checkers on the platform, right? Because the big problem here is that, you know, we are building technology, but we still have to fight with people who are really determined, right? And they are very creative and they are, you know, able to find solutions. So I like to conclude with an analogy that I find insightful about another societal problem that is as important as misinformation, which is car deaths. Why I like this analogy? Because car deaths, it's also about letting the people feel the freedom to drive and do whatever they want, you know, long distance at night, etc. But it's also something that is killing people. And there are many lines. Just follow the red one, please. This is the number of deaths for billions of driven miles, okay, with a vehicle. And you see that over time, from the beginning of this industry, we've been able to do pretty well, right? I mean, it is not a solved problem. I'm not arguing for this, but there is a trend, right? And it's interesting to make the analogy because, you know, there is a problem that impacts the society and the human is in the middle. And it's all this trade-off about giving the ability and putting some restrictions. And it took us 70 years to improve, right? And we did a lot of things. One important thing that we did is that we brought technology. You may be aware of active passive technology. Just to make an example, the safety belt was invented in 1961. However, inventing technology is just one little piece. I'm going to skip this, but just to let you know that in New York, they enforced the law of using the safety belt only in 1984. But there is a law, right? It is not the technology. And the analogy that I want to do is that, you know, to deal with this problem, there are people in the factories coming up with innovation about how to use, you know, technology to solve the problem. But there are also the local police officer, the people taking care of the street or the road conditions. There are people defining the rules, the fact that you need to have a driving license. If you do something, you go to jail, you are responsible. So all these things, it took us 70 years, but we figured it out okay, right? I mean, we all have an understanding of what's going on here. And I mean, my analogy is that we need to find a similar framework also for misinformation. And you know, as computer scientists, I think that our role can be in this space, right? We can say, okay, I see automatic fact checking not as the solution to misinformation, but it's, you know, like the airbag of misinformation. It is not done in the factory, it's done with code, you know, and we have a little piece of technology to help us. But there are still questions, so, okay, who's gonna take care of the rest, right? And finally, in the last few years, we start to see some laws that, you know, they try to put responsibilities and put some information about how to educate people, how to put the providers in a position when they are responsible for what they're doing, but we don't have this level of understanding, right, of who is in charge of what, how to do what. Okay, so I'm going to stop here, and I hope that I give you a feeling of what's going on in terms of computational fact checking driven by the data. and that more research is needed. And I believe that many papers will come out of this, but also that it is not only a problem of technology, but it's a more bigger societal problem. And we also have to push for education and regulation. Thank you.